In this video, we are going to learn the support vector machine classification algorithm. The major advantage of this algorithm with respect to other classification algorithm is that it classifies both linear and nonlinear data. SVM uses a nonlinear mapping to transform the original data, training data, into higher dimension. Within this new dimension, it searches for the linear optimal separating hyperplane, that is a decision boundary separating the tuples of one class from the other. With an appropriate nonlinear mapping to a sufficiently high dimensional data from two classes can always be separated by a hyperplane. The SVM finds this hyperplane using support vectors and margins. And these support vectors are the training tuples in the data set. Now consider the case when the data are linearly separable. A two-class problem where the classes are linearly separable. Let the data set D be given as x1, y1, x2, y2 up to xt, yd, where xi is a set of training tuples with associated class labels yi. Here in this figure, you can see that there are two classes, that is, yi belongs to class plus 1 and or minus 1. Here you can see that the white dots or white circles represents the set of tuples which belongs to positive class, and the black dots represents the set of tuples which belongs to negative class. Now our question is how to find the best one, that is one that will have minimum classification error on previously unseen tuples or the test tuples. There are infinite number of separating lines that can be drawn. Here in this figure, we can see that there are, you can see that 5 different classifiers are drawn over here with dashed lines. Even there are infinite possibilities where you can classify that line. So our question is once again how to find the best one, that is one that will have minimum classification error. If our data were three-dimensional, we would want to find the best separating plane. For example, in this figure, once again in this figure, the data tuples can be separated using a simple line. But for a three-dimensional vectors or for a data tuples with three features or three attribute values, we have to find a plane which separates these data tuple, or the classifier is a plane. For a higher dimension, for even a higher dimension larger than 3, it is called hyperplane. Now consider two classifiers shown in this are shown in this figure, that is a classifier with smaller margin and second classifier with a larger margin. Our question is how can we find the best hyperplane? An SVM approaches this problem by searching for the maximum marginal hyperplane. The associated margin gives the largest separation between classes. Consider the figure which shows two possible separating hyperplanes and their associated margins. Both hyperplanes can correctly classify all the given tuples. Here you can see that both the margins correctly classifies both the data tuples, that is the white class data belongs to positive class and the data belongs to negative class. So this margin separates it accurately, and also you can see that this classifier also separates these data sets accurately. So how to choose the best one? Mathematically, a separating hyperplane can be written as w dot x plus gamma is equal to 0. W dot x is nothing but dot product, or it can be also written as w transpose x plus gamma is equal to 0, where w is the weight vector or called the parameters, and the dimension of w is n dimensional, and x is the input data, which is of n dimension in size. N is the number of attributes, and gamma is a scalar often referred to as a bias quantity. Here we can visualize it once again, that is each data tuple is of size. According to the figure, each data tuple is of size, or it contains two features, and the two features are named as attribute A1 and A2 respectively. That is, a training tuple X can be mathematically represented as x1 comma x2, where x1 and x2 are the values of attribute a1 and a2 respectively for x. If we think bias as an additional weight gamma, we can rewrite the equation as gamma plus w1 x1 plus w2 x2 is equal to 0. So this classifier can be mathematically written as gamma plus w1 x1 plus w2 x2 is equal to 0. Thus, any point that lies there separating hyperplane satisfies, that is, here you can see that according to this classifier, any point that lies above this classifier will satisfy the equation gamma plus w1 x1 plus w2 x2 greater than 0. And similarly, any point that lies below the hyperplane satisfies the equation gamma plus w1 x1 plus w2 x2 less than 0. The weights can be adjusted so that the hyperplane defining the sides of the margin can be written as hypothesis 1 such that gamma plus w1 x1 plus w2 x2 is greater than or equal to 1 for yi is equal to plus 1. Hypothesis 2 gamma plus w1 x1 plus w2 x2 less than or equal to minus 1 for yi is equal to minus 1. That is, any tuple that falls on or above h1 belongs to plus 1, class plus 1, and any tuple that falls on or below h2 belongs to class minus 1. Combining the two inequalities or the above two hypotheses can be combined into a single equation, that is yi into gamma plus w1 x1 plus w2 x2 greater than or equal to 1 for all I. Any training tuples that fall on hyperplanes h1 or h2 defining the margins that are called support vectors. Now, mathematically, the perpendicular distance of the bounding hyperplane w1 x1 plus w2 x2 minus gamma is equal to plus 1 from origin is written as, here you can see that the perpendicular distance of this particular margin to the origin is mathematically written as minus gamma minus 1 divided by square root of w1 plus w2 square, and the distance to w1 x1 plus w2 x2 minus gamma is equal to minus 1 is equal to minus gamma plus 1 divided by square root of w1 square plus w2 square. Therefore, the distance between, that is the distance between these two margins, these two margins as shown in the figure is equal to, we have to take the difference between these two quantities, and it is equal to 2 divided by square root of w1 square plus w2 square, and you know that w1 square plus w2 square is nothing but w1 transpose w2. The aim is to find W and gamma that maximize this distance. At the same time, it should satisfy the matrix constraint equation, that is maximization of 2 by W1 transpose W2 is same as minimization of W1 transpose W2 divided by 2, or half W1 transpose W transpose W. And so the learning problem can be written as an optimization as minimization with respect to W and gamma half W transpose W subject to yk into W transpose xk minus gamma greater than or equal to 1, where k is equal to 1 to n. Consider the case when the data are linearly inseparable. That is, in this figure you can see that the data is plotted such that you cannot make a linear separation between the red dotted points and the blue dotted points. So the SPM deals with such kinds of problem by transforming the current dimensions into transforming the input data points in current dimension to a higher dimension, that is x is transformed to phi of x. So when it is now considered according to this figure, the two-dimensional input samples are mapped to a three-dimensional input sample. So after mapping, you can have a plane which separates this data points. So the non-linear or linearly inseparable data points are dealt by transforming it into a higher dimension, and this transformation is done using kernel function. And mathematically, these kernel functions can be written as kernel of xi, xj is equal to phi of xi transpose phi of xj. There are several kernel functions, out of which three of them are popular. The first one is called polynomial kernel of degree h, Gaussian radial basis function kernel, and the third one is called sigmoid kernel. The expression to these three different kernels are written over here. We can summarize: SVM locates a separating hyperplane in the feature space and classifies points in that space. It does not need to represent the space explicitly simply by defining a kernel function. The kernel function plays the role of the dot product in the feature space. Thank you.